In this video, I'd like to introduce you to aromaticity and to discuss some of the features of a molecule that define aromaticity. And let's start with benzene. So I've already told you that benzene is aromatic and that it is resonance stabilized, and benzene is really considered to be the quintessential aromatic compound, the parent of all aromatic molecules. You may recall that benzene has 6 carbons that are all sp2 hybridized. Each carbon has an unhybridized p orbital. The molecule is planar, so all carbons and all hydrogens in this molecule lie in the same plane. It also has 3 pairs of pi electrons, but rather than having 3 isolated pi bonds, remember that all of the p orbitals are overlapping, so we have in effect a cloud of electron density above the plane and a cloud of electron density below the plane. So if we look at the electron density map for benzene, we see that the electron density is evenly distributed throughout the ring. Now, I told you that molecules or ions that have resonance are more stable than molecules or ions that do not have resonance. So aromatic compounds are exceptionally stable by virtue of having resonance, and we can calculate the resonance energy, or the amount of stabilization, by looking at hydrogenation or reduction. For instance, if I perform this hydrogenation of cyclohexene, this is an exothermic reaction, and it gives off 28.6 kilocalories per mole. So in other words, I can say that cyclohexane is more stable than cyclohexene by 28.6 kilocalories. If I were to perform the same reaction with 1,4-cyclohexadiene, now I have 2 double bonds in the ring. This reaction is more exothermic, and we have release of 57.2 kcals per mole. Well, this actually makes total sense, because 57.2 is equal to 28.6 times 2, so it's exactly twice the amount of energy released as we saw in the hydrogenation of cyclohexene. I can compare energy levels for cyclohexene and cyclohexadiene. So the reduction of cyclohexene gives me cyclohexane with a release of 28.6 kcals per mole. The reduction of cyclohexadiene to cyclohexane releases 57.2 kcals per mole. So if I were to predict the amount of energy that would be released if I reduced benzene to cyclohexane, I would predict that that should be 3 times the amount for the reduction of cyclohexene, right? So it should be 28.6 times 3, or 85.8 kcals per mole. What we actually observe when we reduce benzene to cyclohexane is the release of 49.8 kcals per mole, even less than the reduction of cyclohexadiene. The difference in energy between what we calculate for benzene and what we actually observe is called the resonance energy of benzene, and that is equal to 36 kcals per mole, or I should say minus 36 kcals per mole. What is it that imparts aromaticity to a molecule? Well, there are a number of features that must be present in order for a molecule to be aromatic. This includes an uninterrupted arrangement of pi bonds. The molecule must be cyclic. Each atom in the ring must have a p orbital. The molecule must be planar. And the total number of pi electron pairs is odd. So the number of pi electron pairs can either be 1, 3, 5, 7, and so on. Another way to say this is that the molecule will have 4n plus 2 pi electrons in the ring, where n is any integer. And this is the way that Huckel's rule is stated. So in other words, if n were equal to 1, the number of pi electrons would be 6. If n were equal to 2, the number of pi electrons would be 10, or 5 pairs. If the number were 3, the number of pi electrons would be 14. This makes for exceptionally stable molecules. Well, we know that benzene is aromatic, and it fits all of our criteria. It's planar, it's cyclic, all of the atoms in the ring have p orbitals, and there's 3 pairs of pi electrons, or an odd number of pi electron pairs. Or another way to say that is that in the equation 4n plus 2, n is equal to 1. Let's have a look at cyclobutadiene. Cyclobutadiene is planar, it's cyclic. All the carbon atoms in the ring have p orbitals. However, it has only 2 pairs of pi electrons. So it has an even number of pi electron pairs. Cyclobutadiene is not aromatic. How about cyclooctatetraene? Cyclooctatetraene, it turns out, is non-planar, and that's not immediately obvious. It is cyclic. All the atoms in the ring have p orbitals. It also has 4 pairs of pi electrons, or an even number of pi electron pairs. So neither cyclobutadiene nor cyclooctatetraene fit our criteria for aromaticity. Let's look at cyclopentadiene, the structure in the middle. It has 4 pi electrons, or in other words, 2 pairs of pi electrons. That already does not fit our criteria for aromaticity. It is not planar. Again, that may not be immediately obvious to you. Not all of the atoms in the ring are sp2 hybridized. You can see that we do have an sp3 carbon in this ring. So cyclopentadiene is not aromatic. What about the cyclopentadienyl cation? We have 4 pi electrons, so again, that does not fit our criteria for aromaticity. It's planar. All the atoms in the ring are sp2 hybridized. Remember that I told you that carbocations are sp2 hybridized. But it's not aromatic because it doesn't have the right number of pi electrons. The cyclopentadienyl anion has 6 pi electrons, or 3 pairs of pi electrons, so an odd number of pi electrons, that fits. It is planar. All the atoms in the ring are sp2 hybridized, and that makes the cyclopentadienyl anion aromatic. It may not be immediately obvious to you that the carbanion is sp2 hybridized. However, when sp2 hybridization can result in aromaticity, then that atom will be sp2 hybridized. So we can delocalize that negative charge from the cyclopentadienyl anion throughout the ring by drawing several resonance structures. And if we look at the electron density map, we can see the charge is equally distributed throughout the ring. And like benzene, all of the p orbitals are overlapping, giving us a cloud of electron density above the ring and a cloud of electron density below the ring. What about cycloheptatriene? Cycloheptatriene has 6 pi electrons. The cycloheptatrienyl cation also has 6 pi electrons. But the cycloheptatrienyl anion has 8. So already we can say that the cycloheptatrienyl anion is not going to be aromatic. It has the wrong number of pi electrons. The cycloheptatrienyl cation is planar. Cycloheptatriene itself is non-planar, and the cycloheptatrienyl anion is also non-planar. The cycloheptatrienyl cation has all sp2 hybridized carbons in the ring, whereas cycloheptatriene and its anion, we have in each of those one sp3 hybridized carbon atom. So the cycloheptatrienyl cation fits all of our criteria for aromaticity. So it is aromatic. We can delocalize that positive charge from the cycloheptatrienyl cation throughout the ring, evenly distributing that charge, which is reflected in the electron density map. Unsaturated polycyclic rings can also be aromatic. If we consider naphthalene, the first molecule showing here, we can see that we have 1, 2, 3, 4, 5 pairs of pi electrons. So we have an odd number, so that fits our criteria. Each carbon in naphthalene is sp2 hybridized. The molecule is planar, so naphthalene is aromatic. By that same token, we can see we have 1, 2, 3, 4, 5 pairs of pi electrons in the molecule azulene. Each carbon in these rings is sp2 hybridized, so we have uninterrupted chain or uninterrupted sequence of sp2 hybridized carbons. This molecule is planar, so azulene is also aromatic. Here we have 3 additional polycyclic aromatic compounds, and if we count up our pi electron pairs, we can count 7 in anthracene, 7 in phenanthrene, and 9 in chrysene. All of these compounds are also aromatic.